And that's the point of this afternoon's session, really. We know that a new runway is realistically 10 or maybe 15 years away. So in the meantime, how do we generate additional capacity and a greater resilience? How can we innovate to create that capacity without increased noise, without increasing emissions, without increasing costs to passengers, and without making airports bad neighbours? It is a tough challenge. First, we'll hear from Boeing about advances in aircraft design. Then we'll hear from NATS. Can better management of Southern England's congested airspace deliver more capacity and more resilience? We are promised some very fancy videos, so looking forward to that. After tea, we'll look at the potential for digital data and IT solutions to make airports more efficient, so the Internet of Things, mobile connectivity. If the speakers keep the presentations reasonably short, it will allow for more time for questions and debate, and that would be great. So, with that in mind, can I welcome Mike Sinnett, first of all. Mike is Vice President for Product Development at Boeing. It's all yours.
Thank you. Thank you for being here today. I'd like to spend a little bit of time talking about some of the innovations that Boeing's brought to the market and some of the things that we're working on in the near-term future to try to improve the efficiency of our airplanes and to improve the environmental impact of our airplanes in the world's fleets. There we go. Okay, so each year we look at market trends, we look at economic data from around the world, gross domestic product, gross domestic output of nations around the world, and we develop a 20-year forecast for the need of commercial airplanes throughout the next 20 years. And we divide it into regions in the world, and we divide it among different sizes of airplanes to get a sense of where the market is going. And what we found over the years is that the demand for commercial travel is tied very closely to worldwide domestic output, GDP, and cargo requirements are also tied to that as well. We also know that as we look back to judge ourselves and see how we've done, we are typically conservative and we underestimate the need for commercial jet transport airplanes. Our current market outlook, which was just released last month prior to the Paris Air Show, shows that we believe in the next 20 years there will be the demand for over 38,000 new commercial jet transport airplanes. Half of this output is required to replace airplanes that exist today, in many cases to replace less fuel-efficient airplanes with more fuel-efficient airplanes and with quieter airplanes. But fully half of that output is dedicated to future growth, new demand that doesn't exist today. And as you can see from the chart, on the left-hand side of the chart, nearly 30,000 of these airplanes will be smaller single-aisle airplanes, and nearly 40% will be required for Asia, with the bulk in North America and Europe. So significant numbers of airplanes, and in the past, these outlooks have underestimated the 20-year growth. When I look at the Boeing lineup and how Boeing would choose to address that market demand with our customers, you can see on the left the current lineup of Boeing airplanes, including our newest airplane, the 787-9, which just went into service last summer. On the right side of the chart is the lineup of all of the airplanes that are committed and are in development today, which will all be in service by 2020 or 2021. And all of these airplanes bring improvements in efficiency, reliability, capability, and environmental impact. It's interesting to me to point out as an airplane designer that since the dawn of the jet age, we have been able to reduce fuel burn by over 70% per seat. And we've also been able to reduce the noise footprint of commercial aircraft by over 90% since the dawn of the jet age. These are significant numbers, significant amounts of improvement over time. And we don't just do this with new airplanes. We continue to innovate and bring technology to existing airplanes to improve their performance over time. And a great example of that is the 737. The 737, since it went into service originally, we've reduced the fuel burn of the 737 family by 55% since the airplane first went in service. And we've doubled the number of passengers that the airplane can carry, and we've doubled the range that the airplane can carry those passengers. So just one model, the 737, but significant improvement. And this curve that you see with the 70% improvement in fuel burn is really a reflection of that continued improvement of existing airplanes and the introduction of all new airplanes. I mentioned the reduction in sound and the reduction in environmental noise. And as an example, I've included the view of London's Heathrow Airport, runway 27 right. And this shows the noise contour on takeoff for a number of different airplane types. In the green circle in the middle, you see the 787-8 and its 85 decibel noise contour. And that noise contour is contained entirely within the airport property. And as the capabilities of the airplanes increase and as airplanes get bigger and heavier, the noise footprint tends to grow even for newer technologies. And so one of the things that I think about as an airplane designer is the balance between capacity and the noise that the airplane generates to try to reach a level of most efficient noise reduction for an airport. Sometimes that can be done with increased capacity of airplanes. Sometimes it can be done with improved technology on smaller airplanes, and both of those things working together. Another example at Gatwick Airport, you can see the green circle is the 787, 85 decibel noise contour, and then the 767 300ER, and then the A330 200. So from newer to older technology, the amount of noise that's experienced on the ground grows. When I look at all of the airplanes that we're bringing into service today, the committed new airplanes, they all bring substantial reductions in fuel burn and carbon dioxide emissions over the airplanes they replace. The 777X with a 20% fuel burn reduction over the 777, the 787 with 20% over the 67, and so on. So significant fuel burn reduction and significant emissions reductions as well. But we don't only concentrate on improving fuel burn by improving the airplane technology and the engine technology. We also try to improve the operational efficiency of the airplane by working with air service providers and with airports to design more efficient approaches and departures for the airplanes. Category 3 GPS landing systems is one example of a landing system technology that can help improve airport throughput by improving the ability to land airplanes in sequence in poor weather. We've got projects underway with Norway to improve runway spacing there, precision approach capability trials in China, airport noise assessments in Hong Kong, evaluating the improvements that our technologies can bring, RNP, which stands for Required Navigation Procedure, procedure design in Malaysia, en route efficiency trials in Africa. All of these things demonstrate ways in which we use the technology on the airplane in concert with the airline's operations center, in concert with the airport and air traffic services providers to give us more efficient operational efficiency of the airplane. And a great example of this that just occurred is with Alaska Airlines in Seattle, where we've been able to incorporate RNP approaches to the aircraft landing to the south, so that now instead of a straight-in approach, an airplane can make a curved precision approach over Elliott Bay, which not only decreases the length of the approach and the amount of fuel that's burned on the approach, but it ensures that the noise that's generated on the approach is largely distributed over the body of water, the Puget Sound, rather than over the occupied areas of Seattle. We also have to think carefully about wake vortex generation at the airplane level. As you well know, airport spacing for arrivals typically is influenced by wake vortex strength, and the bigger the airplane in general, the greater the strength of the wake vortex. and the greater the amount of separation that's required between arriving aircraft. Working at the airplane design level, we can change how we distribute lift on the wing to reduce the strength of the vortex at distance. But this is, again, a trade-off between noise and airplane separation. So rather than there being one black and white answer, it's a good example of a case where we have to work a number of different parameters to try to achieve the best overall and most efficient operation at a given airport. Other realms that we work in are biofuel development. As you can imagine, when you burn fuel that was generated by biomass, you're releasing carbon into the atmosphere that was only bound up by that mass 1 or 2 years earlier, as opposed to petrochemicals, where when you burn those fuels, the carbon that's released has been locked up for millions of years. By switching to biofuels, we're reintroducing carbon back into the biomass, binding it up so that the overall contribution of carbon by the aviation system is reduced. We're looking to see more than 1% of demand next year met by biofuel, and we're well on the path to this with over 1,600 flights flown last year with biofuels, and we're in the process right now of working with the industry to qualify green diesel as a source of aviation fuel for blending. We have a program at Boeing called the Eco Demonstrator Program, which my team is responsible for. We've run this program for the last several years, and each year we take an airplane. It started with the 737 and then the 787, and we're just concluding trials with the 757 right now, where we work with a number of partners to incorporate new technologies off of the critical path of a new airplane development. We incorporate those new technologies on a test airplane, and then we develop ways of certifying those technologies and demonstrating that those technologies are robust for the incorporation into an airplane. Some recent examples of some of the work we've been doing on the Eco Demonstrator are advanced aerodynamics for natural laminar flow and sustainability through the use of recycled carbon fiber composites and 3D printing for aircraft components. It's a great program that allows us to bring technology more quickly to bear in an environment that isn't constrained by a new airplane program's time schedule. When we look beyond just the realm of today's commercial jet transports, there are a number of other things that Boeing is doing to try to improve sustainability and environmental performance in the future. We've flown in collaboration with Cranfield Aerospace here in the UK, a subscale blended wing body demonstrator called the X-48. We've worked on a liquid hydrogen-powered aircraft called the Phantom I that can stay aloft for 4 days on a single tank of hydrogen fuel. We've developed fuel cell technology to eventually replace kerosene-burning auxiliary power units on aircraft. And we work with the energy industry in the United States to develop solar energy and other forms of sustainable energy. So it isn't just about the airplane and the engines, it's about the overall system as well. And finally, we work with others, such as those in the UK, on an industry level to figure out ways to collaborate to improve the performance of the system as a whole, so that in the end, we have a more efficient transportation system driven by new technologies with zero growth in emissions, zero growth in waste, and zero growth in water use in the build of those airplanes, all geared towards a better global collaboration to reduce the environmental footprint of our industry. Thank you very much for your time.